So here's the question. Find the length and width of a rectangle that has the given perimeter and maximum area. Okay, so that's kind of annoying. I mean, it's not your question. The way it's written is kind of annoying in that. So I want to find the length and width of a rectangle with maximum area with a perimeter of p units. Okay, well that's kind of awful. And then, So Diana, if you're wondering why you might have got this wrong, because I see that it's at least wrong here, the reason I think you got it wrong isn't because your work is wrong, your answer is wrong. It's because you used a lowercase p instead of a capital P. I think that's the only reason why your answer is actually shown as wrong there, because they used a capital P. And yeah, right, web work can be very, very picky. But let's do the work anyway. So I've got a rectangle. Got a length and a width. And we're trying to maximize the area. So the area is given by length times width. And if you're trying to maximize something, we want it to be a function usually of one variable. But the thing we're trying to maximize is a function of two variables. So we need a constraint. And here our constraint, which doesn't have an M, has an N. Our constraint is that L plus W plus L plus W. Let me close this window. A little better here. That, right, the perimeter 2L plus 2W is equal to P. And so we'll say capital P. So then we're going to isolate one of these variables and plug it into the thing we're trying to maximize. It doesn't really matter here because it's pretty much the same either way. So you can say 2L equals P minus 2W, and then divide both sides by 2. So the L equals P divided by 2 minus W. We're going to plug that in for L. All right, I think I can erase this picture. I don't think we really need more. So then our area equation can now be written as L, which is P over 2 minus W times W. We're going to take the derivative and set it equal to 0 to find the critical values, but I'd rather not use the product rule if I don't have to. So I'm going to multiply this out and say it's equal to P over 2 times W minus W squared. Now it's important to remember that in this context, the capital P is a constant, right? It could be 20 for all we know. I'm just making up a number. But P over 2 is also a constant. So you can think of this as like 20 over 2, like 10W. And the derivative of 10W would be just 10. So the derivative of P over 2 times W is just P over 2. And the derivative of W squared is 2W. And we're going to set that derivative equal to 0. We're also going to think about where it might be undefined, but this derivative is never undefined, so we don't have to. I'm solving for W. P over 2 equals 2W. And dividing both sides by 2 or multiplying both sides by 1/2, we can say that 1/2 times P over 2 equals W. So the W equals P over 4. So 2 questions. So I know this particular question didn't ask it. So, but we should also check and make sure that it's actually a maximum. So there's a few ways you could do this. I'm gonna erase some stuff here. So to check and see it's actually a maximum, you could observe that, well, W has to be bigger than or equal to 0, right? If you've got this rectangle where you've got length, width, length. Doesn't make sense for the width to be negative. Also, the width cannot be any bigger than half the perimeter. Why is that? Well, it's really because the length also should be greater than or equal to 0. So if the length is greater than or equal to 0, then we can see that P over 2 is bigger than or equal to W. Okay, well now, if you plug in 0 for W in the area at 0 is P over 2 times 0. If you plug in P over 2, you get p over 2 minus p over 2, which is 0, times something is 0. If you plug in our critical point, p over 4, I don't know what it is, but I know that p over 2 minus p over 4 is positive. And p over 4 is positive, that's going to be positive. And by the extreme value theorem, which says that on a closed interval, a continuous function, which this is, has to achieve an absolute maximum. Well, since this is the biggest one, because it's the only one that's positive, that's your absolute maximum. So an absolute maximum at W equal to P over 4. If you don't like this, and I wouldn't blame you if you didn't like it, you can also use the second derivative test. Say, okay, well, a double prime, the derivative of this is going to be 0 minus 2. The negative 2 is certainly always negative, which means it's concave down, which means you have a maximum. Okay. In addition to checking that, we also have to find the other critical point, or the other dimension, right? We found that W is equal to P over 4. Now we have to find L. Well, L is P over 2 minus P over 4. So L is P over 2 minus P over 4. That's 2P over 4 minus P over 4, which is also P over 4. Which is not surprising if there's nothing else kind of funky going on. When you're trying to maximize the area of a rectangle, it usually ends up being a square. All right. Let's see. I want to close that. Sorry, one sec. So any questions about this? Oh, no. Before I move on to the next one, are there any questions about this one? Okay, let's move on to the next one. Very emphatic no there, Lauren. All right. No questions. All right. So let's look at this next one. Find the absolute extreme values of the function f of x equal to the square root of 2x minus 2 sin x on the interval. Okay, so f of x, square root of 2x minus 2 sin x over the square root of x minus the square root of 2. That's 2 sin x on the interval 0 to 2 pi. And specifically, we are looking for the absolute extreme values. So this actually dovetails quite nicely with what we were just saying. To find the absolute extreme values, we're going to find the critical points, and then we're going to check both the endpoints of this interval and the critical points in the interval. Just like we did for this previous problem, right? For this previous problem, we have this function, right? The area was a function of W, and on this closed interval from 0 to P over 2, we checked the original function at the left endpoint and got 0. We checked the original function at the right endpoint and got 0. And then we checked it at their critical point in between and got a positive value, meaning that had to be the absolute maximum because it was the biggest of the things. Same idea here. We're going to find the critical values, and then we're going to check our critical values and our endpoints in the original function. Okay. So let's see. I need to find my critical points, and my derivative here is going to be the square root of 2 minus 2 times cosine of x equals 0. So I'm going to add 2 cosine x and say square root of 2 equals positive 2 cosine of x. And then cosine of x is equal to the square root of 2 divided by 2. There's many solutions to this equation, but in the interval from 0 to 2 pi, there's only 2 solutions. One in quadrant 1, where the angle is pi over 4, and one in quadrant 4, where the reference angle is still pi over 4, but the actual angle is 7 pi over 4. So those are the 2 critical values we need to check. And we also have to check 0 and 2 pi. So our job now is to look at f of 0, f of pi over 4, f of 7 pi over 4, and f of 2 pi, and determine which is the biggest and which is the smallest. Okay, so let's see, f of 0 is going to be 0 minus 2 times sine of 0 is also 0. So 0 minus 0 is 0. Okay, pi over 4, so that's going to be kind of funky. You're going to have the square root of 2 times pi over 4 minus 2 times sine of pi over 4 is the square root of 2 over 2. And we'll worry about simplifying these in a minute. F of 7 pi over 4 is going to be the square root of 2 times 7 pi over 4 minus 2 times sine of 7 pi over 4 is negative root 2 over 2 because it's in the fourth quadrant. So it's still the same value, except it's negative as we're in quadrant 4. Finally, f of 2 pi is going to be square root of 2 times 2 pi minus 2 times sine of 2 pi, but sine of 2 pi is 0, just like sine of 0 is 0. Oof. Okay, this is looking kind of gnarly. So let's do a little bit of simplifying. So f of 0 is clearly 0. F of pi over 4, I'm going to factor out the root 2. So write this as root 2 times pi over 4 minus, I'm left with a 2 over 2, which is 1. Notice this number is negative. Pi over 4 is less than 1. Pi over 4 minus 1 is less than 0. So good. Factor out the root 2, I think. Right? I think it'd be really hard to tell if root 2 times pi over 4 was bigger or not than root 2, but it's easier if you factor out the root 2. Let's do the same thing here. I'm going to say that f of 7 pi over 4. I'm going to factor out the root 2. I'm left with the 7 pi over 4 here. And a minus is plus 1 over there. And I know that's bigger than 0. I don't know if it's the biggest thing yet or not. F of 2 pi, on the other hand, is equal to the square root of 2 times 2 pi. So then clearly this is the smallest thing. Which of these is the biggest? Well, what's bigger? 7 pi over 4 plus 1 or 2 pi? It's definitely 7 pi over 4 plus 1. So 7 pi over 4 plus 1 is 7 pi plus 4 all over 4. And this is the square root of 2 times 8 pi over 4. So what's bigger? 7 pi plus 4 or 7 pi plus another pi? Well, definitely it's 7 pi plus 4, right? Because 4 is bigger than pi. So to answer the question specifically, the absolute extreme values are the y values. So I would say that the absolute minimum value is this value here, right? It's the only one that's negative. It's the square root of 2 times pi over 4 minus 1. I would also note that it occurs at x equal to pi over 4. And I know they're not asking that, but this is often we ask the question, where is the absolute minimum? And the answer is, oh, it's at x equals pi over 4. But the absolute minimum value is the y value. And then we would say that the absolute maximum value is this number here. Square root of 2 times 7 pi plus 4 over 4. And it occurs at x equals 7 pi over 4. This is maybe slightly unique in that often when we have an extreme value question on a closed interval, often one of the endpoints ends up being where you have a max or a min, but not always, like in this example. Good question. Questions about this question? You're very welcome. Before I forget, I would love for each of you to quickly fill out this attendance form. It's the same attendance form I have for office hours. If you can all click on this link and fill it out, it's really just, it takes just a moment. Step aside the board. And then if you guys have more questions, you can go over them. Otherwise, I will start doing stuff from the review. All right, we'll jump in if you have something. I'm gonna go ahead and start doing questions from the review, which are lots, right? There's what, 21 questions on this review. Don't imagine I could get through all of it, but we'll see. Let's look at this first one. Evaluate each limit or say why it doesn't exist. Limit as x approaches 4 of the square root of x minus 2 over x squared minus 16. Clearly a 0 over 0 type of limit. And I believe, correct me if I'm wrong, I believe you guys have not covered L'Hopital's rule yet, so can't use L'Hopital's rule. But it is 0 over 0. So what are we going to do? We're going to factor. We're going to write this as the limit as x goes to 4 of the square root of x minus 2 over x squared, sorry, not x squared, x minus 4 times x plus 4. And there's actually two kind of valid directions you can go here. I'll show you both of them. One way you can go is to factor this further and to say that x minus 4 is really the square root of x minus 2 times the square root of x plus 2. Right, it's still a difference of squares. X minus 4 is the square root of x squared minus 2 squared. That's a totally valid way of doing it. You can do it that way. You can cancel these pieces and then say that that's equal to the limit as x goes to 4, 1 over the square root of x plus 2 times x plus 4, and then just plug in 4 and get 1 over 2 plus 2 times 4 plus 4, which is 1 over 32. Another way of doing it, though, would be to multiply the top and bottom by the conjugate. So I can say this is equal to the limit as x goes to 4 of the square root of x minus 2 over x minus 4 times x plus 4, and then multiply the top and bottom by the square root of x plus 2 over the square root of x plus 2. Then when we multiply at the top, square root of x minus 2 times square root of x plus 2 is going to be x minus 4. Right, the first thing squared minus the second thing squared, but this one's canceled. And the denominator, we're not going to multiply that. We're just going to leave it as x minus 4 times x plus 4 times the square root of x plus 2. And then the x minus 4 is canceled, and you get the limit as x approaches 4 of 1 over x plus 4 times the square root of x plus 2. And then we're back where we got to here, where it's going to be 1 over 8 times 4, which is 1 over 32. Either way works. All right, I have a third. Sorry, I was using my black pen just and I thought I had a third good pen here. Oh, maybe it's here. I lost my third good black pen apparently. I'm trying to use these ones. Anyway, actually, I didn't have it. Let's hit it for myself somewhere. Also, a reminder, I will have office hours tomorrow from 10 to 12 and 1 to 3. So if you have questions between now and then that you come up with, feel free to drop on in. It'll be, for the first version, how do they get x plus 4? Oh, sure. So for the first version, so first of all, right, from the bottom, I factored x squared minus 16 is x minus 4 times x plus 4. And then I left the x plus 4 alone, right? This x plus 4 here is still the same as it was right there. What I did is I took x minus 4 and I factored it as x squared of x minus 2 times square root of x plus 2. So that's what happened there. Does that clarify things? All right. All right, let's keep doing limits. This next one looks interesting. The limit as x approaches 2 from the left of the square root of x minus 4. Sorry, plus, no, square root of x plus 2. I feel like I said 4 and I wrote 2. Yeah, I did. square vector without words. Oh, come on. Do that. Sorry, getting black dust all over the floor. It's terrible. Okay. Sorry. Limit of x approaches 4 from the left of the square root of x plus 2 over x squared minus 16. So it looks almost the same as the previous one. The only difference is that now it's a plus 2 on top instead of a minus 2. So whenever you're doing a limit, you should always check what happens when you just plug it in. For the previous one, you plugged it in, you got 0 over 0. We knew we had to do something. Here, when you plug it in, you're going to get 2 plus 2 over 16 minus 16. So you get 4 over 0. So we know that when you have a non-zero number over 0, the answer is one of 3 things. It's either infinity, or negative infinity, or does not exist. Does not exist only happens if it's a two-sided limit, and one side is going to infinity and one side is going to negative infinity. So this is a one-sided limit. Does not exist is not an option. So our job is just to figure out, is the overall fraction positive or negative? Well, clearly the top part's positive. What about the bottom part? I know I wrote 0, which is not a positive or negative number, but technically, right, it's not actually 0. It's a number that's really, really close to 0. So is the number that I have in the denominator slightly negative or slightly positive? Well, I'm picking a number that's a little bit smaller than 4. I'm squaring it and then subtracting 16. So if you take a number that's smaller than 4 and you square it, is it bigger or smaller than 16? It's smaller, right? Like 3.9 squared is not quite 16. So a number that's smaller than 16 minus 16, that's going to be slightly negative. Positive over negative, which means the whole thing's going to be negative. Another way you could look at this one, if you want a little bit more kind of in-depthness, is you could factor the denominator. Factor it as, oh, that's kind of interesting thought. X is minus 4 times x plus 4. That's really interesting. I hadn't thought about that. It's not really important though. So then you can kind of see, okay, the top's going to be 4. A number smaller than 4 minus 4 is slightly negative, which I write as a 0 with a negative superscript. And then 4 plus 4 is 8. So it's positive over negative. That's going to give us a negative infinity. That's how I would do that problem. Okay. Let's look at the next one. Oh, so the next one actually. Oh, okay, the next one's interesting too. The next one is the limit as x goes to infinity of this same expression. And here is the intuition. Taking a limit to infinity, if the biggest power on the bottom is bigger than the biggest power on the top, the limit should be 0. The easiest way to show this here is to divide everything by x squared, or whatever your highest power in the denominator is. So I'm going to write this as x to the 1/2 over x squared plus 2 over x squared over x squared over x squared minus 16 over x squared. Now I'm going to simplify. This is going to be the limit as x goes to infinity of x to the 1/2 over x squared is 1 over x to the 3/2, 2 over x squared, divided by x squared over x squared is 1, minus 16 over x squared. Now as x goes to infinity, 1 divided by x to a power is going to get very, very small, because the denominator is going to get very large. It's going to get small. Same thing here, right? Any number divided by x to a power is going to get really, really small. So I'm left with 0 plus 0 over 1 minus 0, which is 0 over 1, which is 0. That's how we deal with that. Let's look at this next one. Again, if there's certain problems you want me to do in the review, or if there's other things you want to see, just type up. Let's look at this next one. If the limit as x approaches 4 of f of x, I can maybe like the typeface on this is just a little bit smaller than I'm liking. That's much better. Limit as x approaches 4 of f of x, where f of x is given by this piecewise function. F of x is the square root of x plus 3 when x is less than 4. It's 6 when x is equal to 4, and it is x plus 1 when x is greater than 4. So for a piecewise function, to find the limit, the two-sided limit as x approaches 4, look at the limit from the left and limit from the right and see if they're equal. So I'm going to look at the limit as x approaches 4 from the left of f of x, and that's going to be the limit as x approaches 4 from the left of, I have to use the piece where I am on the left side or the less than side of 4, which is that piece right there. The limit as x approaches 4 from the left of the square root of x plus 3. And then I can just evaluate the limit. Plug in 4, get the square root of 4 plus 3, which is 2 plus 3, which is 5. And then I have to do it for the right-hand side. So limit as x approaches 4 from the right, that piece there. So it's going to be the limit as x approaches 4 from the right of x plus 1. Then we can plug in 4 and we get 4 plus 1, which is 5. So the limit does exist since the left-hand side and the right-hand side have the same value, and the limit is 5. Okay, the next question goes along with this. It says for problem number 4, is f of x continuous at x equal to 4? Well, we know the limit exists. That's usually the second thing we check. The first thing we check usually is if the function exists. F of 4 is, well, when x is equal to 4, the function is equal to 6. So the function exists, great. The limit exists, great. But then to be continuous, not only do they both have to exist, they have to be equal to each other. And it is not true, right? F of 4 is not equal to the limit as x approaches 4 of f of x, which means the function is not continuous at 4. Because the limit and the function have different values. Okay, that happens. Not everything gets to be continuous. Look at the next one. Let's see. For what values of b is this following function continuous? So the function is, again, stop me if you have something. I'm just going to keep going. So the function is f of x equal to x squared plus b when b is less than -1. And x plus b squared, that's not right, sorry. When x is less than -1, not when b is less than -1, that's silly. And it's x plus b squared when x is greater than or equal to -1. And we want to know for what values of b is this continuous. So what b values, and there might be more than one answer, make this continuous. Okay, so although it's not super necessary here, I still like to look and say, okay, well, f of negative, oh, I should point. This function is clearly continuous everywhere except for -1. X squared plus a constant, definitely continuous, right? It's a quadratic, it's a polynomial. X plus b squared, that's a linear function, right? It's x plus some number squared. So both of these are continuous everywhere except for where they possibly change from one to the other. Okay, I'll look at that one next learn. So basically, we're only concerned with, is this function continuous at -1? Because we know it's continuous everywhere else. So f of -1, well, I'm going to use the function where it's equal to -1. That's going to be -1 plus b squared. Okay, that exists. It's some real number, right? B is a real number. So I have to look at the limit from the left So the limit is x approaches -1 from the left. Well, I'm going to be using the piece of the function where x is left of -1. So that piece right there. And that's going to equal, so if I plug in -1, -1 squared plus b is 1 plus b. Now look at the limit from the right, and as x approaches -1 from the right, I'm going to be using this piece of the function because that's where x is bigger than -1. And that's going to be, I'm going to plug in at -1 for x and get -1 plus b squared. And now I have to set these two equal to each other because for the function to be continuous at -1, the limit as we approach -1 from the left has to be the limit as we approach -1 from the right. So we're going to say that 1 plus b, let's do this one. Let's do -1 plus b squared equals 1 plus b. This is quadratic, so we should bring everything to the same side. So we've got b squared minus b, -1 minus 1 is -2 equal to 0. This does factor. Factors is b minus 2 times b plus 1. So it looks like our answers are both b equal to 2 and b equal to -1. And this will make it continuous because not only will the limits both be the same, but the function value is also the same as the limit value, right? So if this function value being the same as the right-hand limit equals the left-hand limit, then it's going to be continuous there. So either one of these values, right? If b is 2, you're going to get the value being -1 plus 4, which is 3. This will be 3. This will be 3. If b is -1, you get -1 plus 1, which is 0. This is 0. This is 0. So either way. All right, let's take a look at the question that Lauren wrote. Determine the intervals for which the function f of x equals x to my sine of x is increasing / decreasing. Okay. On the interval 0 to pi, 0 to 2 pi. Here's our function. It is x over 2 minus sine of x. And I want to know where it's increasing, decreasing on the interval where x is an element of 0 to 2 pi, not including the endpoints. At least that's the way it's written there. Which is usually the case if we're talking about increasing, decreasing. I might also look at concavity just because it's usually something we also look at. Well, let's look at increasing, decreasing. So first derivative x over 2 is going to be 1 over 2, or derivative 1/2 x is just 1/2. Derivative of sine x is cosine x. So that equal to 0. So you get 1/2 equal to cosine x. And your solutions are x equal to pi over 3 and 5 pi over 3. The cosine of pi over 3 is 1/2. And then in the fourth quadrant, cosine is also positive, so cosine of 5 pi over 3 is 1/2. So now I have to look at the number line for my first derivative here. So here's my first derivative, and I'm actually really just in between 0, pi over 3, 5 pi over 3, and 2 pi. And the nice thing about cosine function, sine function, well, yeah, in fact, it might be. So I'm going to do it this way, but I'm also going to draw the graph of it. So, not the graph, we'll draw the unit circle. So here's what I know. I know that pi over 3, the cosine value, meaning the x coordinate on the unit circle, is 1/2. The y coordinate is root 3 over 2. And at 5 pi over 3, the x coordinate's 1/2, and the y coordinate's negative root 3 over 2. And notably, here's what I want you to see. In here, the cosine values, which are the x coordinates, cosine of x is greater than 1/2 in this range and in this range. And all in here, which I'll use a different color just to kind of really emphasize it here. Everywhere in here, the cosine value is less than 1/2. Okay. Look at a sine chart. If I'm between 0 and pi over 3, well, I know that cosine is bigger than 1/2. So 1/2 minus cosine is going to be negative because it's 1/2 minus a number that's bigger than 1/2. Between pi over 3 and 5 pi over 3, I'm in this region. 1/2 minus a number that is smaller than 1/2 is going to be positive. You could also pick a point. Right? You could pick, well, between pi over 3 and 5 pi over 3, let's pick pi. Cosine of pi is -1, and 1/2 minus -1 is positive. It's 3/2. And then finally, between 5 pi over 3 and 2 pi, we're in this region where cosine is bigger than 1/2. So this minus cosine is going to be negative. You could also pick something like 11 pi over 6 and cosine, right, which is like right there. And cosine of 11 pi over 6 is √3/2. And then 1/2 minus √3/2 is negative. So we are decreasing, increasing, decreasing. So I would say that we are increasing on the interval from pi over 3 to 5 pi over 3. And decreasing on the interval 0 to pi over 3, union 5 pi over 3 to 2 pi. We could talk about concavity, although it's not particularly interesting here. We talk about concavity. The second derivative is just, well, the derivative of cosine is positive sine. And so the critical points are 0 and pi, and 2 pi, I guess, right? So pi, and then 0 and 2 pi are the ends. And so we know that between 0 and pi, sine is positive. So my second derivative is positive there, negative there. So it would be concave up from 0 to pi, concave down from pi to 2 pi, and you'd have an inflection point at pi. Okay, that's a good question. Yeah, I'm liking these trig questions. They're good. So let's keep going. Next question says, use the limit definition of the derivative to find f prime of x for the following. F of x equal to x over x plus 1. So I'm going to throw the limit definition at it. The limit definition says the derivative is equal to the limit as h goes to 0 of your function of, I should say, f of x plus h, which is just take all your x's and replace them with x plus h's. So that f of x plus h minus f of x all over h. And the trick here, for anything where you've got fractions, like a fraction minus another fraction, is to multiply the top and bottom by the common denominator. The common denominator, unfortunately, is not very nice. It's going to be the product of your two denominators. It's x plus h plus 1 times x plus 1. Excuse me. Over the same thing. So the whole point of doing this is that when we distribute all of this to the first term, the x plus h plus 1 is canceled. And you get the limit as h goes to 0 of x plus h. This cancels that, and you get times x plus 1. Minus x times, now we can't multiply this with this, the x plus 1's cancel, and you get x times x plus h plus 1. Divided by h times all this. And you do not want to multiply out the part that it's not like the common denominator of. So this we just want to leave as is. Okay, we do want to multiply at the top, because again, when we're doing these limit definition of the derivative, our goal is to simplify this in such a way that everything in the numerator that doesn't have an h cancels out. So we can cancel out this original h here. That guy needs to cancel. So it's going to be the limit. That's right down here. It's going to be the limit as h goes to 0. Let's see, I'm going to get x squared plus x xh plus h and then minus x times x is x squared, minus x times h, minus x. All over the same thing, h times x plus h plus 1 times x plus 1. X squared and minus x squared cancel. X and x cancel. And even though xh has an h in it, it still cancels out. So it's okay for some of the h things to cancel. We just want to make sure that for sure all the not h things cancel. But yeah, xh and negative xh also cancel. So then we're left with the limit as h goes to 0 of h over h times x plus h plus 1 times x plus 1. H divided by h leaves me with a 1 on top. So now I have the limit as h goes to 0 of 1 over x plus h plus 1 times x plus 1. And here we can see that now we can take the limit. This only h here is going to go to 0. So we're left with 1 over x plus 1 times x plus 1, which is 1 over x plus 1 squared. Great. All right. Let's look at the next one. Just keep going. If you have any other questions, you can always send them my way. Let's look at this one here. So find the derivative of each function. You need not simplify your answers. So let's look at this first one. F of x is equal to 1 over 2 times 3x plus 4 to the 5th. Plus x times the square root of x plus pi cubed. And definitely the intent behind this problem is that you simplify it before differentiating it. I'm just going to simplify. I'm going to write this as 1/2 times 3x plus 4 to the negative 5th. I really don't want to use the quotient rule here unless I have to, and I don't have to. And then x times x to the 1/2 is x to the 3/2 power plus pi cubed. Okay, so a couple things here. When you're simplifying this, you're not doing any differentiating. So you don't want to write plus 0 here. I know the derivative of pi cubed is 0 because the derivative of constant is 0, but it's wrong to do part of the derivatives and part of the simplifying at the same time. You're either just simplifying or just differentiating. So now we're ready to take the derivative. So my 1/2 constant is going to hang out because it's a multiple, times the derivative of some stuff to the negative 5th is -5 times our stuff to the 1 less power, -5 minus 1 is -6, times the derivative of the inside stuff, which is 3, plus the derivative of x to the 3/2 is 3/2 times x to the 3/2 minus 1 is just 1/2. And finally, the derivative of pi cubed is 0. Right? Pi cubed is like, I don't know, 30-ish about. Derivative of 30 is 0. So that's all there is for part A. I think we can fit part B in here, yeah. So part B, your function is f of x equal to sine to the 6th of 5x plus 4 cubed. Okay. Specifically when you have a power of a trig function like this, sine to the 6 or cosine cubed or tangent squared, I really recommend rewriting it as sine of whatever you've got here, 5x plus 4 cubed, all raised to the 6th power. So that it's really obvious that when you use the chain rule, what function's on the outside. So my derivative here, I've got some stuff to the 6th power. My derivative is 6 times that stuff to the 1 less power. But now I have to multiply by the derivative of the inside stuff. derivative of sine of some other stuff is going to be cosine of that stuff. So the derivative of sine of 5x plus 4 cubed is cosine of 5x plus 4 cubed times the derivative of the inside stuff. The derivative of the inside stuff, the derivative of 5x plus 4 cubed is 3 times 5x plus 4 squared. Right, there is some stuff cubed is 3 times your stuff squared times the derivative of the inside stuff. The derivative of 5x plus 4 is just 5. Kind of a pain. Let's look at the last part of this question 6. Let's see. Sorry, not 6, 8. F of x is equal to x times secant of x over cotangent of 3x. You could rewrite this as x secant of x times tangent of 3x and use the triple product rule, but I think I'd rather just leave it as is because I feel like that's kind of the point of the problem. So f prime of x is going to be at the bottom, cotangent of 3x, times the derivative of the top, which is going to require the product rule. So the derivative of the top is going to be derivative of x is 1 times leave secant x alone, plus x times the derivative of secant x, which is secant x tangent x. Minus, now we flip it. We do instead of the bottom times the derivative of the top, we do the top times the derivative of the bottom. The derivative of cotangent of 3x is negative cosecant squared of your stuff times the derivative of your stuff. So negative cosecant squared of 3x times 3. All divided by cotangent squared of 3x, or the denominator squared. And the problem said don't simplify, so I'm not going to simplify, even though I kind of want to. All right, so problem 10. All right, that was problem 9. That was problem 8. It's problem 9. Okay, problem 9 says find the equation of the tangent line to x squared plus 2xy plus y squared equal to 9 at the point 0, 3. So we're trying to find the equation of the tangent line. We have a point, we need a slope. How do we find the slope? We take the derivative. Specifically, we take it implicitly here. So differentiating both sides, we get derivative of x squared is 2x. The derivative of 2xy, we have to use the product rule. So it's the derivative of 2x, which is 2, times leave y alone. And then it's 2x times the derivative of y, which is the derivative of y. The derivative of y squared, or some stuff squared, is 2 times our stuff times the derivative of the stuff. On the other side, the derivative of 9 is 0. Now, normally, if they said, here's an equation, find the derivative of y, we would group these on the same side, we would bring this stuff to the other side, we would factor out the y prime, we divide and solve for y prime. But they didn't say we had to find y prime. They said find the equation of the tangent line. All we have to do is find the slope of the line at that point, or I should say the slope of the tangent line at that point. So plug in 0 for x and 3 for y. 2 times 0 plus 2 times 3 plus 2 times 0 times y prime plus 2 times 3 times y prime equals 0. Well, that goes away, and I've got 6 plus 6y prime equals 0, 6y prime equals negative 6, y prime equals negative 1. So at the point 0, 3, the slope is negative 1. And then we can use the point slope form to say that, oh, the equation of my line is y minus 3 equals the slope times x minus 0. I would probably simplify this. I'd probably write this as y minus 3 equals negative x, or y equals negative x plus 3. So yeah, when you're doing implicit, and you have to find, if you're doing implicit to find the slope of the tangent line, as soon as you take in the derivative of both sides, you can immediately plug in your point and solve for y prime. It's usually much easier that way. Let's take a quick bathroom and get a refill on water break and meet back at 11 o'clock sharp. So we'll take like a 3-minute break and we'll be right back at 11. Sorry, I'm getting a new pen to have more good ink. All right. So, continuing on. An ant on the ground is 5 feet from the point where a toy rocket is fired straight up into the air at a constant rate, 2 feet per second. Okay. There's an ant. On the ground. And it is 5 feet away from where a toy rocket is going to be fired straight up in the air. So over here, there's a toy rocket. Welcome, Max. We're just working on problem 10 from the final review. If you have questions, feel free to ask them either in the chat, send me an email, or even say words. And if you can fill out that attendance form when you have a second, that'd be great. We're working on problem 10 here, which is there's an ant on the ground. It's 5 feet from where a toy rocket's going to be fired straight up in the air at a rate of 2 feet per second. So the question that's asked first is how fast is the distance between the ant and the rocket changing 6 seconds after the rocket's fired? So the rocket's going to be going up this way. It's going to be up some higher point up here later on. And we want to know, okay, so this distance here is 5 feet. We want to know how fast this distance is changing 6 seconds after it's been fired. And this height, we don't know what it is, but we know that it's changing, right? The height of the rocket is increasing at 2 feet per second. So usually when we're doing these related rates problems, our first point of business is to say, okay, what's changing? What do we want to know what's changing? We know that dHdt is 2 feet per second. At the rate of change of height of the rocket is 2 feet per second. Speed is 2 feet per second. And we also know that we want to know how fast the distance between the ant and the rocket is increasing. So we want to know what is dsdt. Specifically, we want to know what dsdt is after 6 seconds. But we don't plug in that until after we've done all the other work. So then we need an equation relating the variables that we are interested in, specifically height and s. So I'm going to use the Pythagorean theorem. 5 squared plus h squared equals s squared. There's my equation. And then after we find the equation relating the non-time variables, we take the derivative of both sides. The derivative of 5 squared is 0. The derivative of h squared is 2h times dh dt. Right? We're differentiating with respect to time. So the derivative of some stuff squared is 2 times your stuff times the derivative of your stuff. Similarly, the derivative of s squared is 2 times my stuff times the derivative of the stuff. Okay, now we need to plug in what we know. So we want to know what's going on at time equals 6 seconds. Well, there's nowhere in any of these equations to plug in time equals 6. We have to use the fact that we know what things are at time equals 6. So we know that after 6 seconds, well, if dHdt, if the speed is 2 feet per second, for 6 seconds, then the distance is going to be 12 feet. So we're going to get 2 times 12 feet times dHdt, which is 2 feet per second, equals 2 times, okay, well, s. If h is 12, s is going to be 13, because we have a 5, 12, 13 right triangle. Or you could solve it, right? 5 squared plus 12 squared equals s squared. 25 plus 144 is s squared. That's 169. So s is the square root of that, which is 13. So if you see a 5, 12 as the legs of your triangle, the other side is going to be 13. That's going to be 13 times ds dt. Divide both sides by 2. Divide both sides by 13. To get ds dt is equal to 24 divided by 13 feet per second. Okay. The second part, or the second question in this problem is, how fast is the angle of elevation between the ant and the rocket changing at the same instance? So how fast is this angle changing? So to answer that, now we're interested in finding what d theta dt is. So we're going to go back to the drawing board. You say, well, I don't really care about ds dt anymore. Now I want to know what d theta dt is. So to figure that out, instead of getting an equation now that relates the height and this distance s, I want an equation that relates the height and this angle theta, and preferably not s. So I'm going to use a trig function. That's almost always how we relate an angle and one of the sides of triangles, a trig function. And I'm going to pick tangent of theta. Tangent of theta is opposite over adjacent, which is h over 5. Great, I have only the variables I want, none of the variables I don't. And I would probably do one other thing. I would probably rewrite this as 5 times tangent theta equals h. So now we're going to differentiate both sides. Derivative of 5 tangent theta is 5 times secant squared theta times d theta dt. And the derivative of h is dh dt. Now we're going to plug in. dh dt is still 2 feet per second. D theta dt is what we're trying to find. And secant squared, well, so I still know it's at the same moment, it's still 6 seconds later. So this is still 5, this is still 12 feet, and this is still 13 feet. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. That's going to be 13 over 5 squared. I might simplify a little bit. I might write this as, I don't know, maybe not. I might just solve for d theta dt and say d theta dt is 2 divided by 5, and dividing by this is multiplied by its reciprocal, so it's going to be times 5 squared over 13 squared. So you can cancel a 5 here and a 5 here. You can get 10 over 169 radians per second. So that's how fast the angle is increasing. It's increasing at 10 over 169 radians per second. All right. Sorry, 1 second. Oh, I forgot my water. 1 second. There we go. So, let me see where I'm at. Problem 13. Find the absolute extrema. This is similar to a problem that Lauren asked, but not quite the same. And the absolute extrema of f of x equal to sine squared x plus cosine x on the interval from 0 to 3 pi over 2. So same kind of process. We're going to find the critical values. So f prime of x, so derivative of some stuff squared is 2 times your stuff times the derivative of your stuff. So the derivative of sine squared is 2 times sine times cosine. Plus the derivative of cosine is negative sine. So that equal to 0. Solve. Factor out of sine x. Left with 2 cosine x minus 1 equal to 0. So either sine x equals 0, which gives you x equal to 0 and pi, and not 2 pi because it's not in the interval. And here you're going to get cosine x equal to positive 1/2, which is going to be x equal to pi over 3, and would also normally be from 0 to 2 pi at 5 pi over 3. The 5 pi over 3 is quadrant 4, and 0 to 3 pi over 2 is only quadrants 1 through 3. So we only get those critical values. So we need to check all of them. So these 3 critical values and these 2 endpoints, except one of them is the same. So we'll just so f of 0, sine of 0 is 0, cosine of 0 is 1. F of pi, sine of pi is 0, cosine of pi is negative 1. Pi over 3. Cosine of pi over 3 is clearly 1/2. Sine of pi over 3 is the other value, root 3 over 2. That's going to be root 3 over 2 squared plus 1/2, which is going to be 3 over 4 plus 1/2 is 2 over 4. It's going to be 5 over 4. And then 3 pi over 2, sine of 3 pi over 2 is negative 1, so that's going to be negative 1 squared. And then cosine of 3 pi over 2 is 0, so that's 1. So the maximum value is 5 over 4. The minimum value is negative 1. Okay. Let's look at 14. Again, I don't know if I sent this to you, Max, but no, I think I did. But right, if any of you have any other questions you want to see, please don't hesitate to let me know. Right in the chat, you can email them to me. So let's see here. This is problem. I just went past it. Oh, sorry, I skipped a problem. I skipped like 2 problems. I skipped problems 11 and 12. I don't know how I did that. So let's go back to problem 11. So if the surface area of a cube is increasing at a rate of 72 cubic feet per minute, so the surface area of a cube is increasing 72 square feet. Sorry, I think I said cubic feet. Apologies. how fast is the volume increasing? When each, cut off some of this here accidentally. Sorry, let me make this a little bit larger. When each side is 3 feet. Okay, so let's draw a cube. And we're saying we know that the surface area is increasing at 72 square feet per minute. So ds dt is equal to 72 square feet per minute. We want to know what dv dt is. So we want to know what's the volume. So we need an equation for volume as a function of surface area, which is kind of atypical. Right? We know the volume of a cube is x cubed, if you call each side x. And the surface area of a cube is, well, each side is x squared, and there's 6 of them, so it's 6x squared. So I want to write volume as a function of surface area. So I guess what I'm going to do is I'm going to solve this for x. So x squared equals surface area divided by 6. So x equals the square root of surface area divided by 6. So my volume equation is x cubed. That's going to be the square root of s over 6 cubed. I'm going to simplify this a bit. That's going to be s over 6 to the 3/2 power. So now let's find the derivative. Taking the derivative of both sides with respect to time, dv dt equals, here's some stuff to the 3/2 is 3/2 times your stuff to the 1/2. But then we have to multiply by the derivative of stuff, and the derivative of s over 6 is 1 over 6 times ds dt, right? This is really 1 over 6 times s, and the derivative of that is 1 over 6 times the derivative of s, which is ds dt. Okay. So we end up getting, so sorry, that's our dv dt. Now we're going to plug in, right? We know that s is equal to 72. So we're going to 72 divided by 6 times 1/6. Sorry, 72 divided by 6 to the 1/2 power times 1/6 times ds dt, which is 72. This doesn't come out to be very nice. We end up with, let's see, 72 divided by 6 is 12. So we end up with dv dt is equal to 3/2 times 12 to the 1/2 power times 12. And 12 times 3/2 is going to be 18. So it's going to be 18 times the square root of 12. And that's going to be cubic feet per minute. You could probably do more simplifying here. I do want to look at my answers just to make sure that I feel like that seems like kind of a funky answer. So let's double check and make sure that I'm not making a dumb mistake. So I'm going to look at those solutions real quick. So I'll make sure I'm not leading you down the wrong path here. I'm just always a little wary when my answers have kind of strange numbers. Yeah, apparently I did make a mistake. Let's take a look. Yeah, all right. What did I do wrong? I did something wrong, but what? Oh, I see what I did wrong. So I made a kind of I don't want to say a classic error, but a very typical error. So for ds dt, I plugged in 72 because the rate of change of the surface area was 72 feet square per minute. But for s, I also plugged in 72. And that actually wasn't right because the surface area isn't 72. We are asking how fast is the volume increasing when each side is 3 feet. So when each side is 3 feet, the surface area is actually 6 times 3 squared, which is 6 times 9, which is 54. So this actually should have been 54. Sorry about that. It should still be S there, sorry. That's going to make things a little bit nicer. And let me talk about a different way to do this problem as well. So that's going to give us 3/2 times 54 over 6 is 9. The square root of 9 is 3 times 1/6 times 72 is 12. That's going to be a lot nicer. That's going to be 3 times 3 times 6. That's going to be 9 times 6 is going to be 54. Another way you can do this is you can actually find what dx dt is first. So let me just do this on the other side so we can compare our answers. So if you know that the surface area is changing at 72 square feet per minute, and you know that the equation for surface area is 6x squared, you can differentiate both sides of this and say ds dt equals 12x times dx dt. Then you can plug in 72 for s, ds dt, and 3 for x, and then say, oh, dx dt is just 2 feet per minute. Then you can say, okay, well, then we know that volume is x cubed. So dv dt is 3x squared times dx dt. And then instead of trying to have to plug in surface area equal to 54, you can just say, oh, well, we know that when surface area is 54, right? Well, we know that x is 3, and we know that dx dt, we just found it was 2. So we get 3 times 3 squared times 2, which is 27 times 2, which is 54. So that also works. It's a little weird. Let's look at the next one. Sorry, I know I skipped some problems here. Let's look at problem 12. So sometimes if you've got like an area and the volume that both depend on a thing like x or like the radius, sometimes it just makes more sense to figure out what is going on with the thing they both depend on than trying to relate them. It still works, it's just sometimes easier to do it the other way. All right. So let's see here. What have I got? Problem 12. The height of a ball, or excuse me, the height s of a ball in feet t seconds after it's been thrown straight up from the top of the building is given by s of t equals negative 16t squared plus 32t plus 48. So that's the height of the ball at time t. So times 0, we get 0 plus 0 plus 48. So times 0, the ball's height is 48. And actually, that's the first question. What was the height of the building? So if you're throwing it from the top of the building, the height of the building is the position at time 0, which is exactly 0 plus 0 plus 48. 48 feet. Second question. What was the initial velocity of the ball? Well, the velocity of position, or the velocity of an object is the derivative of its position. So if we find the derivative, s prime of t, which is v of t, that's going to give us negative 32t plus 32. And if we find an initial velocity, that's the velocity at time 0. So we want v of 0, which will be 0 plus 32. So 32 feet per second. Okay, third part. What was the maximum height of the ball? So to find the maximum height, well, if you're trying to maximize the height, trying to maximize a function, you find its critical values. Take its derivative, set it equal to 0. So we're going to set the velocity equal to 0. That makes sense, right? Because if the ball is going up, the velocity is positive. It tops out, and then it starts going down, the velocity is negative. And so when it goes from going up to going down, it goes through a point where the velocity is 0, and that's the maximum height. So setting this equal to 0, we get 32 equals 32t, so t equals 1. Now that's not our final answer. That's just the time when we reach the maximum height. We have to plug that back in to the height or position function to get the S of 1 is equal to negative 16 times 1 squared plus 32 times 1 plus 48, which is negative 16 plus 30, or I should say 32 plus 48 is 80. 80 minus 16 is 64 feet high. And the last question I'm sure is, yeah, what's the velocity of the ball as it strikes the ground? So to find the velocity when it hits the ground, you first have to find what time it is when it hits the ground. That is the time when the height or the position is 0. So we're going to set the position, negative 16t squared plus 32t plus 48 equals 0. And someone has been nice, we'll set this up so a negative 16 factors out. And it does. Negative 16 factors out, leaving behind a t squared, a minus 2t, and a minus 3. This factors as t minus 3 times t plus 1. So either it strikes the ground 3 seconds after you throw it, or negative 1 second. So 1 second before you throw it. Well, that doesn't make sense. It's 3 seconds after you throw it. So then we want to find the speed at which it hits the ground. So the velocity at time equal to 3. That's going to be, well, let's see, my velocity equation is right there. It's going to be negative 32 times 3 plus 32. That's going to be negative 96 plus 32, which is negative 64 feet per second. Purely coincidence that the maximum height is 64 feet and the speed we hit the ground at is negative 64 feet per second. Just a coincidence. All right. Again, do stop me if you have questions, both about anything I've said or about other things. So let's look at the next one. At problem 14. Find the area of the largest rectangle that can be inscribed inside a semicircle of radius 1. Now, I know we've already done a problem like this before, so I think I want to show you a different way of doing it that I think might be a tiny bit easier. You might disagree, I don't know. So we've got the semicircle of radius 1, and I want to find the area. Actually, let me read the question again very carefully. Find the area of the largest rectangle that can be inscribed in the semicircle of radius 1. So not the dimensions, although we could find the dimensions, but specifically the area. So one way to do this is to say this corner here is the point x comma y. The height of my rectangle is y, and the length of my rectangle is actually 2x, because this is x and this is y. So one way to say, okay, area is 2xy, and then the equation of the semicircle is y equals the square root of 1 minus x squared. And then you can plug that in for y, and you have to differentiate it into the product. Well, it's kind of a bit messy. Another way to do this is to say, hey, well, look, this angle here, I'm going to call this angle theta. And I can see that sine of theta equals the opposite of our hypotenuse, which is just y over 1, which is y. And cosine of theta is the adjacent of our hypotenuse, which is just x. And so the area, instead of equaling 2 times x times y, is 2 times cosine theta times sine theta. And now I'm going to take the derivative of this. So the derivative, right, because it's already written as a function of one variable. So I'm going to write it as sine theta times cosine theta just to make it a slightly bit nicer. So let's see, the 2 is just going to hang out. Product rule for sine theta, cosine theta. So your sine is cosine times cosine plus sine times the derivative of cosine, which is negative sine. So I end up with 2 times cosine squared theta minus sine squared theta equal to 0. So I basically want this to equal this. So I want cosine squared theta to equal sine squared theta, or taking the square root of both sides. You can take the square root of both sides, or you can divide both sides by cosine squared. Either way, you can say dividing by cosine squared, tangent squared theta equals 1. So tangent theta is plus or minus 1. And the angle where tangent is equal to 1 is pi over 4. So you can say pi over 4, or 3 pi over 4, et cetera, et cetera, et cetera. But the only angle we really have to consider is pi over 4. Because if we're thinking about this point being in this first quadrant here, the angle has to be between 0 and pi over 2. So pi over 4 is our critical point. It does give us a maximum. Because if you look at the, I really don't want to do it, but if you look at the second derivative here, like you think, fine. If you look at the derivative there, the derivative cosine squared is 2 cosine theta times negative sine theta. Right, derivative stuff squared is 2 times your stuff times your stuff. Minus derivative sine squared is 2 sine theta times the derivative of, that's going to be, no, that's fine. Times the derivative of sine theta is going to be cosine theta. And if you look at this, this is negative 2 sine theta cosine theta minus 2 sine theta cosine theta, which is going to be negative 4 times negative 8 sine theta cosine theta. And if you plug in pi over 4, that's positive, that's negative. So the whole thing is negative. It's concave down, never mind. All right. So anyway, theta equals pi over 4, and the area is 2 times sine of pi over 4 times cosine of pi over 4, which is 2 times the square root of 2 over 2 times the square root of 2 over 2, which is 2 times 2 over 4, which is 1. Interesting thing I've noticed when you ask this question. If you're asked what's the area of the biggest rectangle that can go in a circle of radius blank, the answer is that the area is blank. So if the circle has a radius of 1, the biggest rectangle has an area of 1. The circle has a radius of 5, the biggest rectangle has an area of 5. Kind of interesting. In the semicircle, I should say. Okay. So Lauren, I think I literally just did that problem. Right, or at least a little bit ago. That was the problem I did, I think. Yeah, even with the square. Yeah, I definitely did that problem. It was problem 11. No, sorry, not 11. It was problem 13, where I did the same function, but you are right. I didn't talk about where it was increasing or decreasing. So I can look at that real quickly if you want, right? Because I was doing the extreme values. So let me just look back at that question real quick, because it is a different question that you're asking. So, right, for f of x equal to sine squared x plus cosine x on the interval 0 to 3 pi over 2. It is funny though that it's virtually the same question, but not exactly. The derivative was 2 sine x times cosine x minus sine x equal to 0. We factored out the sine x up to 2 cosine x minus 1 equal to 0. And you get x being 0 and pi. Here you get x being pi over 3. Because you want cosine x to equal 1/2. So then on your number line, you get 0, pi over 3, pi, 3 pi over 2. And that's kind of the it, right? I'm looking at the sign of our derivative. So here's our derivative. So I'm going to try and pick angles I know how to deal with. Like between 0 and pi over 3, I can pick pi over 4. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2. So this is 2 times root 2 over 2 minus 1. That's going to be root 2 minus 1, which is positive. So between 0 and pi over 3, it's positive because it's a positive times positive. between pi over 3 and pi. Yeah. So I'm going to think of a number close to pi. Oh, pi, no, that's fine. Sorry, pi over 3. Yeah. We can pick like 2 pi over 3. Sine of 2 pi over 3 is positive. Cosine of 2 pi over 3 is negative. So that's a negative minus 1, still negative, and the negative times the positive is negative. Finally, between pi and 3 pi over 2, we can pick 4 pi over 3. Sine, well, or basically you'd say we're in quadrant 3. Sine is negative, cosine is negative. A negative minus 1, still negative, so a negative times a negative is a positive. So it's increasing, decreasing, increasing. So it's increasing 0 to pi over 3, union pi to 3 pi over 2, decreasing pi over 3 to pi. That's how you do that one. You're welcome. All right, let us look at 15. So let's see, 15 here. You're designing a rectangular box with a square base that needs to hold 32 cubic feet. So here's my rectangular box with a square base. So the base is square, meaning those are both x, and the height, let's call it y. So the idea here is that, so let's read the rest of the question. If the material for the top and bottom of the box costs 4 times as much as the material for the sides, find the dimensions of the most economical box. So we want to minimize the cost. And the cost is equal to, well, I know that whatever the sides cost, and so the sides, right? So the sides are, each of them is xy, there's 4 of them, so the sides are 4xy. And the top and bottom is x squared and another x squared. I know that the top and bottom cost 4 times as much as the sides, right? So I basically just need to multiply this by 4. Now I'll give you my cost equation. Right, maybe the sides really cost $2 per foot, per square foot. So the top bottom would cost $8 per square foot, and it'd be 2 and 8 here. Then I could divide both sides by 2, so it wouldn't really matter. So yeah. And then we have a constraint that the volume, which is x times y, has to be 32. All right. So we're going to take our constraint, solve for one of the variables, probably the one that's easier. In this case, I would solve for y. We're going to plug that into the thing we want to maximize or minimize. In this case, minimize. So I'm going to write that the cost is equal to 4x times 32 over x squared plus 2x squared times 4, or just 8x squared. How about that? And it is worth our while to simplify a little bit first. So 4 times 32 is 128, and x divided by x squared is x to the negative first. So now let's differentiate. Our derivative here is negative 128 x to the negative second plus 16x. Set that equal to 0. Now we're going to solve. So 16x equals positive 128 times x to the negative second, or divided by x to the positive second. Multiply both sides by x squared, so 16x cubed equals 128. Divide both sides by 16, so x cubed equals 128 divided by 16. 128 divided by 16 is 8. So x is the cube root of 8, which is 2. Okay, is that a minimum? Let's check the second derivative. C double prime is negative 128 x to the negative second plus 16x. We plug in 2, C double prime at 2, I get negative 128 times 2 to the negative second, which is times 1/4, or divided by 4. plus 16 times 2. Uh-oh, that's a problem. That's going to equal 0. What a bummer. So the problem with that is that that means the second derivative test is actually inconclusive. It doesn't actually tell us if it's a max or a min. It still could be a min and probably should be a min. But unless I'm making some mistake here, let me double check. My second derivative is, let me see it one more time. It's negative 128 times x to the negative second plus 16x. You plug in 2, you get negative 128 divided by 4. Oh, that's no, I did make a mistake. Okay, we're good. Making mistakes. Plus, no, wait, no, I take it back immediately. Negative 128 divided by 4 is definitely 32. So it's negative 32 plus 32, which is 0. Okay, so that means we need to do something else to see if it's a max or a min. So the other thing we can do is we can do the, let's see. So if we look at the cost function, then we're trying to see if it's a max or a min. If we look at it like this, yeah, okay. So what I have to say. So what's the domain of our cost function? Well, our function is 128. I mean, you know what? I wasn't making a dumb mistake. Sorry, my brain's getting a little tired. The mistake I was making was I was taking the derivative of the original function to find the second derivative. Yeah, right. I was taking, yeah, sorry, I was blowing it there. So let's be a little more careful here, James. Our first derivative is negative 128 x to the negative second plus 16x. And then, yeah, and clearly if we plug in 2 here, we're going to get 0 because that's how we found the critical value. If I take my second derivative, it's going to be positive 2 times 128 is 256 x to the negative third plus 16. You plug in 2 there, you get 256 divided by 8 plus 16, which is certainly positive, which means we do have a minimum. Sorry about that. Okay, so x equals 2. And the question, I believe, asked us to find the dimensions for the cheapest box. So if x is 2, y is going to be 32 divided by 4, so y is going to be 8. So those are the dimensions of the cheapest box where the top and bottom cost 4 times as much as the sides and holds a volume of 32. All right. Look at problem 16. Problem 16 gives us the function f of x equals x cubed times x minus 4, which I would also multiply out as x to the 4th minus 4x cubed, and asks us to graph it, including all the things. So I would start with the intercepts. Y-intercept, f of 0 is 0. X-intercept, set the function equal to 0. You want the factored form. X cubed times x minus 4 equal to 0. You get x equal to 0 and x equal to 4. Polynomials don't have asymptotes. So let's move on to the first derivative stuff. Sure, the first derivative. Again, I want to use the unfactored form for that. It's 4x cubed minus 12x squared. But then I do want to factor it to find the critical value. So factor out 4x squared of x minus 3. And then setting each of those equal to 0, you get x equal to 0 and x equal to 3. First derivative test also tells you where it's increasing, decreasing. Pick a number larger than 3, positive, positive. Between 0 and 3, positive, negative. Left is 0, positive, negative. So it's decreasing, decreasing, increasing. We have a relative maximum at the point 3, comma f of 3, which is 3, comma f of 3 would be 27 times negative 1, so negative 27. Second derivative stuff. So we're going to use the unfactored form to find the next derivative. F double prime is going to be 12x squared minus 24x that equals 0. Factor out of 12x, you're left with x minus 2. So then x equals 0 or 2. Number line for the second derivative. Pick a number larger than 2, like 3, positive, positive. Between 0 and 2, positive, negative. Over here, negative, negative. So it's concave up, concave down, concave up. So you have inflection points at 0, 0, and 2 comma f of 2 would be 8 times negative 2, which is negative 16. So the graph of this would look like, let's see, we have intercepts at 0 and 3, sorry, 0 and 4. And we know it's decreasing, decreasing, increasing. We have a minimum at 3, negative 27. It's going to look like this. So it's decreasing, concave up, decreasing, concave down. At 2, the concavity changes to being concave up, and then minimum like that. This line looks a little straighter than it should. It's a little curvier. Much better. Okay, to the next one. Next one, we have to graph more things. Let's see. Next one, we're being asked to graph a thing, but they're giving us the first and second derivative. So this one, they're telling us that, let's see here. F of x equal to x to the 5/3 minus 5x to the 2/3, which I'm going to factor to see, since I'm going to factor out an x to the smallest power, so x to the 2/3, I'm left with x minus 5. And they're also telling me that the first derivative is 5 times x minus 2 over x to the 1/3. The second derivative is 10 times x plus 1 over 9x to the 4/3. And finally, they're also telling me that f of 2 is equal to approximately negative 4.76. Okay, so let's find all the things. Intercepts. Y-intercept. Set x equal to 0. You're going to get y equal to 0. X-intercepts. You set y equal to 0. That's for the x-intercept. You get x to the 2/3 times x minus 5 equals 0. So you get x equal to 0 and x equal to 5. Okay. First derivative stuff. You set this equal to 0 / undefined. Your critical values are going to be 2 and 0. Okay, so that's why they're telling me the f of 2 is that, because it's going to be a max or min and it's hard to calculate. So if I do the number line for those critical values, I have, let's see, so big number bigger than 2, like 10, positive, positive. Between 0 and 2, let's pick 1. 1 minus 2 is negative. 1 to the 1/3 is positive, so it's negative overall. Pick something like negative 1. Negative 1 minus 2 is negative, and negative 1, the cube root of negative 1 is negative, so positive overall. So increasing, decreasing, increasing. It looks like we have a relative max at 0, 0. We have a relative minimum at 2, negative 4.76. Okay, second derivative stuff. So if this equal to 0 / undefined, the critical values are going to be x equal to negative 1 and 0. Because again, 0 makes it undefined. So picking something larger than 0, like 2, positive, positive. Between 0 and negative 1, so let's pick negative 1/2. Negative 1/2 plus 1 is positive. -1/2 to the 4/3 power. Well, the cube root of a negative is still negative, but the 4th power of a negative will turn it positive. So it's going to be a positive over a positive. So it's going to be positive still. And then over here, left of -1, like a -2, we've kind of determined the bottom is already always positive because it's to an even power, which makes it positive, and the cube root keeps it positive. But negative on top, so it's going to be negative. It's going to be concave down, concave up, concave up. So this we have an inflection point at -1, comma. You plug in -1 to the original function, you get -1 to the 2/3, which is +1 because it's squared, which is 1. Cube root of 1 is 1. And then -1 minus 5 is -6. So 1 times -6 is -6. The other thing to note before we start graphing this is that at 0, the derivative is undefined. Meaning that even though the function is defined at 0, we probably have some sort of like vertical tangent line thing happening. We'll try graphing this and see what happens. So let's see. I've got the point 0, 0, and 5, 0, and so I have point 0, 0, and 5, 0. Let's see, what else did I have? I also had, from the first derivative, I had 0, 0 again. That's a maximum. Let me just draw this over here. So I've got my 0, 2, 0, right? 0, 2, 0, and it's positive, negative, positive. So increasing. And then I also have the second derivative, -1, 0, and it was, what was it? It was, let's see, down, up, up. Okay. So we had the point at -1, -6. Sure. All right, so check this out. So it's increasing until we get to that point, decreasing afterwards, and increasing after 2 comma -4.76. Okay. So 2 comma -4 3/4 about. So this one's kind of bizarre looking. So up until this point, it's concave down. So it's kind of like, and I'm gonna scooch this up a little bit so it's not so terrible to draw. So I'm gonna change this a little bit. I'll show you what I mean. So like, let's just not label the y-axis over here. So basically it's concave down until you get to -1, and then from -1 to 0, it's concave up. So you guys can kind of see that, right? The concavity changed. And then after 0, it's going down and it's concave up. So there's this whole change of direction. And then we get to the point 2 comma -4.76. I know my graph is really not to scale. That's okay. And then after this point, it's increasing and still concave up. Beautiful. Okay. Let's look at this last graphing one here. So number 18, we're going to graph f of x equal to x plus 3 over x squared. And again, we're given some information. We're given the derivatives. So we're given that f prime of x is negative quantity x plus 6 over x cubed. And that f double prime is 2 times x plus 9 over x to the 4th. Okay, so let's find all the things. Y-intercept, there isn't one because you can't plug in 0. X-intercept, set the top equal to 0, and you get x equal to -3. Okay. Vertical and horizontal asymptotes. You definitely have a vertical asymptote at x equal to 0. You also have a horizontal asymptote. Since the degree on top is less than the degree on the bottom, the horizontal asymptote is 0 as well. First derivative stuff. Let's just make the number line. So my critical values for my first derivative are -6, and I'm going to include 0 even though it's not really a critical value. It's still important. So I get -6 and 0. Pick a number larger than 0, like 1. Man, I got partial listen. Sorry. Okay, so pick a number larger than 0, like 1. Top is negative, bottom is positive. Between -6 and 0, like -3, that's negative, so it's positive overall. -7, that's going to be negative and negative, so positive, and negative down here, so it's going to be negative overall. Decreasing, increasing, decreasing. So we have a relative minimum at the point -6, comma. If you plug in -6, you get -3 on top and 36 on the bottom, so -112. And you don't have a relative maximum at 0 because it's a vertical asymptote at 0. Okay. Second derivative stuff. We're going to get -9 as a critical value and 0 as a pseudo critical value. To the right of 0, if you plug in 1, positive, positive. Between 0 and -9, plug in -1, positive, still positive. But to the left of -9, like -10, negative, positive. So it's concave down, concave up, concave up. So an inflection point at -9, comma, plug in -9, you get -6 over 81, which reduces to -2 over 27. Okay, let's graph the thing. So let's see here. X-intercept, let's see, -3, -6, -9. Okay. So x-intercept at -3. And then we have a relative minimum at -6, -112. And then we have an inflection point at -9, -227. And since this is a minimum, the stuff to either side should be above it. So I know that that inflection point is a little bit higher. So then we have a horizontal asymptote at 0, so it's going to look like this. So from -infinity to -6, it's decreasing. From -6 to 0, it's increasing. We have a vertical asymptote at 0. And then from 0 to infinity, it's decreasing. We have a horizontal asymptote, so we have to flatten out like that. There's our graph.